Good afternoon, everyone. My name is Saskia Vardos Walton, and today we will present to you what we've learned at LHPU. To my right is Bhushan, and to my left is Rohit. In this course, we've learned about sensors and hardware and implementation of the autonomous vehicle. But first, we'll give you a brief background about ourselves. So I'm a recent graduate from Eastern Michigan University. I have a master's in computer-aided engineering and a bachelor's degree in mechanical engineering. My work experience has been a mechanical design engineer making medical devices. I've also worked as a research graduate assistant to increase the manufacturing throughput, cycle time, and reliability in the manufacturing environment. I was intrigued about the autonomous vehicles and wanted to be more a part of the industry of the future and shaping it. And that was why I joined LHPU.
Hi, a little bit about my education. I have a master's degree in mechanical engineering at IUPUI. I have specialization in mechatronics and controls. Little bit about my experience. I got an opportunity to work for an organization in transportation and autonomous system institute at IUPUI, where I was a research assistant. I got to work on projects like occupant safety system for Ford Autonomous Project and variable data acquisition system for Toyota Autonomous Project. One of the things which I really enjoy at LHPU was to code the things and write the algorithms and see them in action on our projects, RC car or the pod.
Hey everyone, my name is Bhushan Deshpande and I am a master's student in automotive engineering with a specialization in autonomous vehicles. My experience relates to vehicle and robotic autonomy, and I have been a research assistant at robotics lab in Clemson for 1.5 years now. And I've also been a graduate engineer in a tier 1 supplier company for 1 year before that. My work details entail to being a lead for autonomous racing team in IROS 2020. I have also a research publication in autonomous path planning, as well as I have developed industrial pick-and-place robot applications for industry. My motivation to work in the field of autonomy comes from developing softwares and seeing them run on the real vehicles. Now that we have completed the introduction part, let's go over the overview of the autonomous system stack. We have 5 different things here, which we worked through in the LHPU course. We started with sensors, then localization and perception, then planning, then controls, and then actuation. Sensors help us to see the world around us. Localization and perception help us to understand the world around us, as well as to locate where we are in the surroundings. Planning helps us to go from one place to the other in the surroundings. Controls helps us to develop and send the steering and throttle commands to the vehicle. Actuation actually deals with the wheels and the steering of the vehicle.
Now that we have seen a good overview of how the autonomous system or process works, we'll go into a little deep what sensors we use for our application at LHPU. 3 of the main principles which we have on the sensors are ranging sensors, photovoltaic effect, and trial iteration. Let's go a little deep into one of each sensors. So one of the widely used and the one which we use for our application sensor is LIDAR. LIDAR is a ranging device which it throws a light, and whenever it is reflected back, it gives us the distance of that particular reflected object. The things which we developed at LHPU while experimenting with LIDAR was reactive planning and mapping. Bhushan will explain it a little bit about that.
Yes. So we use the LIDAR for mapping using a technique called simultaneous localization and mapping. We used an algorithm called HectorSlam to map the room around us as well as localize where the LIDAR is in the map.
As you heard Bhushan mention, that mapping is very important. Therefore, we combination with reactive planning. LIDAR has a 360-degree angle, and as you can see in the image, we've broken it into 3 different sections. We have our frontal view, our right and left, and this allows the car to pursue on its path and avoid obstacle detection.
Yes, one of the other things which we did was to keep the car at the center of the lane so that it will be perfectly at the center. This was a little bit about the LiDAR. Let's move to the next sensor, which was camera imaging. We used a Logitech camera and we actually mounted that on our RC car and tried some experiments on that. The programming language which was used was Python. We used libraries like OpenCV and many functions which was related to that. We used a perspective transform which actually made us look through a bird's eye view, which made a better lane detection for the car. A little bit about the video is going to explain that.
So in the video, you can see that the car is traveling across the yellow lanes in a figure of 8 loop, which is this was the test track that we developed for testing this algorithm.
So as you can see in the second video, we have our camera following a lead. And for this, we developed an algorithm, which was for color detection. And we also used, in order for the camera to follow the track, we did another algorithm for lean detection. And if you look closely in the video, you'll see the signals that the commands are given from the vehicle, where it's turning right, left, or to go straight.
Yes, this was a really good sensor which we used, and we learned a lot about this. We'll move on to the next sensor, which was the GPS sensor, which we did some trial experiment on. GPS is something which let us know the car's position in our global positioning system. The normal use for that is Google Maps, which we use on the foot. What experiment we did using GPS sensor is going to be by Saskia.
So as you can see in the visualization example 1, we have our GPS mapped out. What we did was we went to Milry's Park, loaded our vehicle with 3 different types of GPSs. As you notice on the loop here that we've created, we have the RTK GPS, which is in white, we have the VFAN, which is in yellow, and the GMOS, which is in red. The RTK GPS proves that there is more accuracy in result of following that path opposed to the other 2. Therefore, for an autonomous vehicle following this, we need the most accuracy results for navigation.
Yes, one of the other things with the RTK, if we closely look at, it was trying to be in the center of the lane, and it was really accurate for that. That was one of the test experiment which we did. The next experiment, I think we faced a little problem while collecting these data, and yes, Bhushan is going to talk about it a little.
Sure. So this was an interesting problem which you can see on the image on the right. A car is taking a left turn here, and you can see the differences as Saskia mentioned. There are 3 different GPS collecting data at this point now, and the car is turning left, but the data that is being given by 3 different GPS is very different. You can see that the yellow and the red spots are very far away from the actual turn of the car, whereas the RTK GPS is giving an accurate and precise localization.
Yes, this gives us an overview that how important is it for the GPS sensors to be accurate on the lane for autonomous systems. Now that we have covered all the sensors, how we use the GPS, camera vision, and LIDAR sensors in our experiment, let's move on to the next topic, which would be the perception part of it.
So now we've covered sensors, we want to understand in how it makes our vehicle aware of the surroundings. And in this one, we're going to specifically understand how the camera works and view what it's seeing. So in this here, we have the camera using as perception for machine learning. We want our vehicle to understand these images that we have here, which is the traffic signals. For example, in the first image, we have a stop sign, and in the second, we have a right, and then in the third image, we have both combined together. What we want is our vehicle to understand these, receive these images, interpret it, translate it, and then perform the action that needs to be done. For example, when it comes to the third image, as you see the stop sign and right sign, we want our vehicle to understand that the stop sign has the highest priority before taking the right turn. So it must stop and then proceed with the right turn. And now that we've wrapped up an understanding of how the camera operates, we will now take this further into our planning operation that we've conducted.
Yes. So let's talk about planning after we have covered sensors and perception, which helped us to see the surrounding around us as well as understand the surrounding around us. So let's take a look at planning. In this section, we are looking at rule-based planning, which we did in the LHPU course. Here we are looking at different rules which are laid out on the test layout. And Saskia would like to explain more about the testing layout that we did.
So as you can see, we've constructed this testing layout. We have 2 exits, if you notice, one on your right and then one further at your left. And in each intersection, we have some traffic signs. I don't know if you can see them, but there's a stop sign to your left. Forward is the 2 combined together are right and stop, and then there's an obstacle avoidance. So what we're going to happen here is that we're going to have our vehicle follow the yellow line, which is our lane, and once it comes to an intersection, it must produce a command to say stop and then proceed, follow in the next path, and at each intersection, and keep going forward and so forth.
Thank you, Saskia, for telling us that. Now let's look at the testing, the tests that we performed using this testing layout. So here you can see the testing layout, which is the exact replica of the physical model that we did. This is a digital version of that.
Yes. So one of the tests which we performed, this was the first test scenario for us in which the car was set on the path, and it has to do all those, it has to carry out on all those modes, which is mentioned, like it has to be only right, only stop, stop and right, and obstacle avoidance. Obstacle avoidance mode, if there is no sign or no input from any other senses, it should just go there and take a deflection or avoid the obstacle. That's what the first scenario was, friends.
Yes, and now that Rohit has explained about the first test, let me explain more about the test 2. Here we tried to confuse the car by placing the different signs on the track however as we wanted. That actually intended to do the confusion part on the test layout, but the car turned out to be pretty robust in understanding the situation and acting according to the rule. Let's have a look at how the car performed in both of these tests. So here you can see the car, both the videos of the car. Saskia, why don't you explain about the first video?
So yes, as you can see in the first video, we placed our vehicle on the track, and as it comes to the intersection, as I mentioned before, it is translating that information of the traffic sign and then proceeding with that command of what to do next, and then following the path again and keep repetition.
Yes, on the right side of the video, we can see that the computer interface, what's going on the computer and computer side of the project. If you can see closely on the video, there is a gray image and there are some color image. The color image is one where it is going into the lane detection mode, and the gray image is the one which it goes for sign detection and obstacle avoidance.
Yes, thank you, Rohit, for elaborating in the video, and thank you, Saskia, as well. Let's take a look at the solutions and the challenges actually that we faced in the next slide.
One of the main challenges which we faced while completing this particular scenario was the computation power. Since we had machine learning module, LIDAR module, and camera vision running on that processor, it was taking about 97% of its memory. So we needed to divide those processes into some two so that it will operate properly. We used Jetson Nano and Jetson TX to dividing those processing power. We used the DOS master and slave protocol to join them and then transfer the data from one to another. One of the pros which we had while using this was improve the performance.
Yes, but the performance improvement does not only depend on increasing the compute power. It also depends on whether your algorithm is robust enough or not. So to make our algorithm robust, we reduce the false lane detection by changing or tweaking the algorithms, as well as increase the prediction accuracy for the stop and the right sign.
So another challenge we also faced was developing the algorithm that will have a human-like mind, and where we wanted to think like an actual human being, where as I perceive an image, I know automatically what to do, and therefore developing that algorithm for the vehicle to stop, see the lane, and proceed again, and then move to the next option of turning right.
Yes, and performing those solutions for the challenges we faced, one of the cons which we had was the card has increased in the weight.
Yes, and that increased weight was because of the additional processes that we used, which also caused an additional power consumption, which was one of the cons. Now that we have looked at the challenges, solution, as well as the entire test demonstration that we made in the planning section, let's move on to the next section, which is the controls.
So as Bhushan mentioned, we've covered the path planning, and now we're going to move on to controller. So we know we need our vehicle to have send commands for our throttle and steering. And we're using a widely known application, which is the PID controller, which we implemented into the car sim software. And for this, it allowed us to tune the parameters and see the performance of our vehicle. And the task here is to allow the vehicle to follow a path, stay in its lane, reach a specific destination while speed managing itself.
Yes, to perform those tasks, the approach which we used was to tune the proportional and derivative gain on the controllers. And the objective here was to push the vehicle to its dynamic limits so that it will achieve the task at as early as possible, as fast as possible.
And as a result, we obtained that the car was able to maneuver at a speed of 130 kmph in a record time of 5.55 seconds. On the graph on the right, you can see the blue line is the line of the lane change, and the red line is the line of the vehicle trying to keep up with the lane change.
So now that we've covered this, we're going to look at our simulation videos that we've done in car sim. So in the first two images, or videos that we have here, we have a frontal view and an aerial view, which Bhushan will clearly explain.
In the both of these videos, you can see the car drifting from the main line and coming back to the original line. But this has caused a lot of rider discomfort because the lateral acceleration is too much here.
Yes, and since it is going to, we are approaching to the actual limit of the car, we can see that there is a drift in the motion of the car also.
And now that we've covered the controller system for the PID, we're going to move on to another controller system we use, which is called the Stanley controller. And what we've done here in this slide is that we took the GPS results that we collected from Millway Race Park and implemented this to make our controller, which Rohit will explain.
Yes, so one of the objectives to use the Stanley controller and the approaches which we used was whatever the data we collected from Millway Park, where we actually drove the car and collected the data on the GPS. We got those data and then we fed that to our Stanley controller, where Stanley controller output was the vehicle heading and distance. What that exactly means is which direction the car is moving and how much is it keeping up with the path which is given to it. And distance is the actual error of how much far is it from the actual path. And those were the inputs given to the Stanley controller, and we got the vehicle heading and distance from the actual path from the output of the Stanley controller.
And so now you have an overview of our controller. We're going to show our results that we've collected.
So in this image, you can see the actual result of the Stanley controller. The black line is the GPS waypoints that we collected, as Rohit mentioned, and the dotted or dashed red line is the actual vehicle simulation of how closely the vehicle follows the black line with the Stanley controller.
So as you see, Bhushan mentioned our first results that we've accumulated, and now we'll move on to our second result, which Rohit will explain further.
Yes, as Bhushan explained that the dotted line was the path which the car was taking. We have this as a cross-check error, which we can see there is a reference line from 0, and there are some deviations of those graphs, which means that the car was trying to keep up with the actual track. These were the errors which we got, and it can be seen that there is a little bit of errors in this, and we are planning to correct that or improve the performance after we start our internships at LHPU.
So now that we've covered controllers, we now move on to our actuation hardware implementation for our vehicle. So as you can see in the first slide image, we have here is the Jetson Nano and the Jetson TX2. And these two act as the brains of our autonomous vehicle, which will store and process the information.
After processing the information, we also need to send that information to the actual actuation hardware, which is wheel and steering. This is done by the electronic speed control shown on the second image top, and the servo drive shown on the second image bottom.
Yes, and to perform communication between the processing unit and the driver, which is Jetson Nano and ESC, we use a CAN J1969 protocol, where the components used were breakout box and Quasar links, which actually made those interface between those two, processing unit and driver.
And now that we've covered actuation hardware, we'll now move on to our Capstone project.
Yes, after collecting all this information of sensors, what localization is, perception, planning, and controlling, and after the actuation hardware, we got this. The goal of this Capstone project was to collect all those data, use all those concepts, and then try to implement something on the perception pod, which we have in the image.
So as you can see in the image here, our perception pod is that the vehicle is equipped with several different sensors. And at the top we have, in the purple is the camera, in the orange the GPS, the green the sonar, and in the front the red is the radar. And what is happening here is that with all these sensors combined together, it's creating a sensor fusion, allowing your vehicle to be fully aware of its surroundings and to perform a proper navigation.
Yes, and after having the perception and localization set up, we have the onboard controller which we interfaced and use that to enable the autonomous drive in the perception pod using the GPS data.
Yes, after we have seen what the goal and the approach was, we'll see what the actual experimental setup was for our Capstone project. The video on the left, you can see there is our perception pod, which is riding its path through Millway Park Lane, and it's trying to maneuver around and collect all the waypoints of the GPS, and then we are going to store those GPS points and send into the car's memory, and then we did a simulation video of that. Firstly, why don't you talk about it?
So as you can see in our simulation video, we have collected our points, and in those points, we have in our vehicle to follow that track of points around the system there. And once it completes its system, it comes back to its stop area.
Yes, this was the experimental setup and the simulation which was going on computer or the car end of it. We'll get to see how the actual working or what the car was doing as what simulation we did.
So on the video on the left, you can see the steering wheel control using drive-by-wire system. We had set throttle to a constant value and only controlled the steering using the onboard controller that we had. And this is the video of working steer-by-wire system, which you can see on the video on the left.
So as you noticed in the video on the right, we have sonar. And like I previously mentioned, the vehicle is equipped with several different sonar sensors. And with the sonar, it has a safety margin detection of something is in front of it. So for example, Rohit stands in front of the vehicle is already detecting that there's something in front of it, and it's going to maintain that margin distance. Once Rohit backs away, the vehicle will continue to proceed on that path, but once it increases on that safety margin again, the vehicle will come to a stop. And now that you have an overview of our presentation, we would like to conclude and thank you for your time on watching us present. And if you have any questions, please feel free to ask them.
Thank you.